If peas that are heterozygous for both tall stems and green seed pods are crossed, the probability is that 75% of the offspring will be tall. The probability is also that 75% of the offspring will have green seed pods. What is the percentage of the offspring that are likely to be tall and have green seed pods? Well, for a problem like this, where we're given percentages, we actually have a really easy job. What we need to do is just multiply those percentages. Now, you may remember from math, when you're ready to multiply using a percent, you actually have to turn it into a decimal. So by moving the decimal 2 places to the left, we get 0.75, and we're ready to multiply with it. So 0.75, which is 75% of the number 1, multiplied by 0.75, because those are our two percentages given in the problem, will give us the percentage of having both these traits, and that is the number 0.5625. And that means that it's this fraction of the number 1, which would be 100%. So in order to make this a real percentage again, we just move the decimal 2 places back to the right. So our final answer is that 56.25% chance of being tall and having green seed pods for these plants. A yellow guinea pig is crossed with a white guinea pig. All of the offspring are cream-colored. The cream-colored animals are crossed. 16 yellow, 33 cream, and 15 white animals are born. Explain these results, and explain how a white breed could be developed by starting with 2 cream-colored parents. Draw a Punnett square to illustrate your explanation. Okay, well, we start with a yellow guinea pig and a white guinea pig, and just so that I make sure that this is understood, I'm going to start with that cross. So this is the F1 generation here. So we have the yellow at the top and white at the bottom, and when we cross these, you'll see that all of the offspring have the same genotype. They're all big Y, little y. That's the letter I chose. And that tells me that all of these are cream. And now what I can do is take that heterozygous genotype and set up another Punnett square. So I'm going to make both parents heterozygous, big Y, little y, and set up the cross. Now what we see here are some different genotypes. I see one that is totally homozygous dominant, and that would be yellow. I see 2 that are heterozygous, and that would be cream, so 50%. And then I see 1 that is homozygous recessive, and there's only that 1. And that sounds about right, actually. When I look at the numbers we got, 16, 33, and 15, that is pretty close to 1 to 2 to 1. Now you might say, well, why isn't it perfect? It doesn't have to be perfect. Remember, Punnett squares are just possibilities, probabilities. We're not going to get exactly 1 to 2 to 1 every time. Now, if we were to use very, very large numbers, it would work out even closer, but this is very close. Explain why you would be able to differentiate between a heterozygous and a homozygous dominant individual with the same phenotypes by crossing each with a homozygous recessive individual. Okay, well, let's pull out the key information from this problem. We see that we've got heterozygous and homozygous dominant. Now, what this means is we can't tell just by looking at an individual with a dominant trait if they are heterozygous or homozygous dominant. So what we're doing here is crossing it with a homozygous recessive individual. Well, this should be familiar. This is just a test cross where you take an unknown and cross it with the homozygous recessive trait. So if we were to set up a Punnett square, assuming it was homozygous dominant, and we cross it with the homozygous recessive trait, we would see that all of the offspring would be heterozygous. They would all be the same. Now, if we were to do a cross with a heterozygous dominant trait and the recessive trait, we would see that only half of the individuals would have that trait. So we can tell the difference by how many of their children have the certain trait we're looking for or not. So again, if they are homozygous dominant, all of the offspring have the dominant trait. If they are heterozygous, only half of the offspring will have the dominant trait. And that's how we know what the individual is. We have to use the test cross and look at the offspring. Use the probability of products rule to determine the following. The probability that both parents will be carriers of cystic fibrosis when the incidence of carriers among the general population is 1 in 20. So this means that out of everyone you see, 1 in 20 of those people could be carriers of cystic fibrosis. So what we have to do here is a lot like when we multiply percentages, but this time we're multiplying these fractions. So we start with 1 in 20 people that could have this gene. So the odds of one person who has it meeting and marrying another person who has it and then producing offspring Well, it's just 120 times 1 over 20. So 1 over 20 times 1 over 20. And we're just multiplying that out. So you would put 1 times 1 is 1 on the top, and 20 times 20 is 400, and that goes on the bottom. So that gives us a 1 in 400 chance that two people would both happen to be carriers that actually come together. So it's a pretty rare chance, actually. Even though it's kind of prevalent in the society, the chance of coming together is pretty small. Now we're going to use that same basic problem and now calculate the risk of a couple having a child with cystic fibrosis when, in order to have the disease, the child must be homozygous recessive for the trait, and then explain your answer. Well, we're going to have to do two things here. We need a Punnett square, and we're going to multiply fractions again. So we'll start with our previous problem. We knew that the odds of those two people even coming together is 1 in 400. So now we're dealing with that 1 in 400 chance couple and looking at their chances of having a child with cystic fibrosis. So if I set up a Punnett square with the carrier parents, which is very rare, 1 in 400, we just use a big letter and a little letter, and we set up the Punnett square. I see that the only child that could have cystic fibrosis is the totally recessive one in the bottom corner. So I'm going to use the fraction 1/4 because only 1 out of 4 has that trait, and that's cystic fibrosis. So I take that number and I'm going to multiply it by the chance that we would even have these carrier parents in the first place. And we calculated this number from before, and it's 1 out of 400. So 1 times 1 is 1, 4 times 400 is 1600. So the chances of a couple having a child with cystic fibrosis, this couple has just met from the regular population, the chance is 1 in 1600. So essentially, these are your chances for marrying somebody who's a carrier, for yourself being a carrier, and for having a child with this disease. It's a 1 in 1,600 chance.